All right, it's our precise definition of a limit. Um, it's a heck of a thing. It's also known as the delta epsilon proof, or epsilon delta. That's a lowercase d, lowercase e in Greek. Now this is a little much, a little soon. We're just learning what a limit is. We learned our left hands or right hands. Kind of limit from the left and limit from the right and go to the same spot, then the actual limit exists. But this is actually like the math behind it, more the proof. So this might be our first opportunity to do a real math, an actual proof, instead of just computing things like we usually do. So let's jump in and see what's going on. And oh my. Yeah, so you just read right through, huh? Just read it, and then you're gonna understand it. You'll have no problem. You know, just like your history class, right? It's the same thing, right? You just read it and memorize it. Just like sociology, same thing. Psychology, same thing. Of course not. STEM's a pain in the ass. Just because you read it doesn't mean shit. You might have to read it 10, 15, 20, 30 times before it actually makes any sort of sense. And even then it might not make sense. So give yourself a break throughout this section. Take your time. Look at this stuff not just once, but maybe twice or 3 times. There's going to be a process you're going to follow, but we're not talking about this in this first video. I'm just kind of introducing it a little. Not much intro here. So let's talk. So let f be a function defined on some open interval that contains the number a except possibly at a itself. Remember this? Remember interval notation, like -1 to 3 or something? Those are x values. So we're saying our a is somewhere in between some open interval, some x values. I don't know, maybe it's -1 to 3. Maybe it's 1,000 to 3 trillion. I don't know what the frickin' thing is. That's all that's saying. So then we say that the limit of f of x as x approaches a is L. Then we write, this shouldn't be too different from us, right? Where f of x and our L, our y values go right there. And then our x values go underneath the limit. Our x tends towards that a. And both L and a are just freaking numbers, like 7 and 2 and 100. They're just a number. Now that's the stuff that should be kind of okay. But this is where we all get weird. This is the formal definition. So for every number, for every number epsilon greater than 0, some positive number. So if this limit's true and everything's good, if you come up with some positive number, then there must be some other number delta, some positive number delta, such that the difference, the absolute difference, or the distance away from each other between x and that a value is less than delta. It's also positive. Then we can guarantee that our outputs will be close enough together. You know, close enough, epsilon close, less than that small freaking number, and that actually proves it. Now that made tons of sense, huh? Super simple, right? Super simple. So make sure to put in the same amount of time into your homework in calculus as you do in your sociology or psychology class, because they're the same, right? Heck no, you do all the reading and you still don't even know what the heck's going on. You gotta learn the process. This stuff is wonky. So here's just a little graph. You're gonna see another video on this next. I'll actually kind of go through and do some stuff, but here's the game. Let me get rid of all my little color coding and crap like that. Purples go with Y's. Blues are going with your X's. So what if we were to look at some sort of limit? Some limit is x tended towards 3 of some function 2x minus 1 is equal to 5. We'll delve more into this in the next video. And this is kind of giving us some sort of thought on what's happening here. It's saying if you want to, we got some little epsilon we can add and subtract from this height. See that height, that y value for where we want that limit to go to? See the L? See that? So there's some little epsilon, some sort of number we can add. So I don't know, maybe your boss is like, I need that shit to be within 1 away from 5. And you're like, all right, well, I guess the epsilon's equal to 1. So this would be 1 and that would be 1. You need to leave a little gap. So I think that's equal to 6, and this would be equal to 4. So you're like, shit, I need my outputs between 4 and 6, or my frickin' boss is going to fire me. Now, what frickin' inputs? What inputs? How close to the 3 do my inputs need to be? That's the game. So your delta is saying, how frickin' close? That's how close to A it needs to be. Your epsilon is how close your output needs to be to that L. Look, we got a little right here. See our graph? See our graph that's going through right here? When we're talking about the x values, it's on that graph. When we're talking about f of x, it's on that graph. L and A are just freaking numbers. So we're saying, let's get that shit closer and closer. This is our basic game. You tell me how close you want to be to that output, and I'll tell you what you need to do with your inputs to make sure that happens. Terms like tolerance. Possibly, let me give you some sort of a shitty real world example, saying that, let's say on some sort of graph here, we have, this would probably be pretty linear. It'd probably be pretty linear. I don't know. Where this is going to be taste happiness. Because I'm going to eat a frickin' cake, dude. Taste happiness. And this is going to be the amount of frickin' sugar you put in there. Well, there's going to be some sort of oomph. You put too much frickin' starts off. You don't give me enough sugar, I'm not going to be frickin' happy. You start putting in too much sugar, I'm not going to be frickin' happy. Now, the only place that I'm good with it, it's got to be at least to here. Or I ain't eating that shit. You know what I mean? I ain't eating it. It can be up to here. Up to there, I'm just going to fall down, and I'm just not going to be able to make it. It's going to be too freaking happy. Well, where the hell do we need to keep the sugar inputs to be? Like, there's a whole host. You can make it pretty, not that sugary, I'll still eat it. You can make it pretty darn sugary, and I'll still eat it. But you put no sugar, I ain't eating that shit. You pour in the whole bag, my teeth are going to fall out. So we'd say that there had to be some sort of, oh, okay, so from here to here. You're like, look, I got to keep my X values. I need to keep this amount of freaking sugar to make sure that it's edible. It's a delta epsilon. The input being the amount of sugar, the output being how your mouth likes it, huh? So hopefully that made a little bit of sense. Maybe. In the next one, you'll learn a little bit more into how, not quite how. By the third one, we'll get you the full directions on how to start solving these problems, because they're going to pop up on your test. We gotta know how to run through it. But don't worry, this is a short thing. We mess around with it, and then it's in the past, and then you can talk about how much you didn't like it, but it'll be in your rear view. So, all right, I'll see you in the next one.